In this video, we demonstrate how place image data collected from the air and the ground delivers actionable insights in a matter of days to address pressing urban and environmental challenges, whether population growth, transportation planning, waste management, service provision, or flood mitigation. Without up-to-date information, decision makers find it difficult to answer questions like, how green is my city? How many people live here? As they work to improve livelihoods, mitigate the effects of climate change, and advance the UN Sustainable Development Goals. So how can Place's high-resolution imagery help? Well, used in combination with machine learning, or AI, which can automatically detect objects in images, for example cars, buildings, and trees. And not surprisingly, Meta's machine learning tool is called the Segment Anything model. Place imagery provides the starting point by which informed decisions can be made. So to answer the question, how green is my city? Decision makers can make use of Place's high-resolution imagery to map parks and trees. Place imagery collected once is extremely cost-effective as it can be used for multiple use cases across multiple agencies, departments and ministries, with no duplication of effort. After all, the same image can be used to map roads if you're the Department of Public Works, or parks if you're the Department of Recreation, or schools if you're the Department of Education. So let's take a look at some of the use cases that place imagery can be used for. These examples use locally collected data in combination with off-the-shelf software and machine learning tools that run on standard computers, requiring minimum training. Let's start with the first question. How many people live here? Malawi has a growing, youthful population with around 60% under 24 years of age, so knowing where people are, made more difficult by a lack of up-to-date maps, is essential in planning for things like education and employment. Zomba, in the south of Malawi, is a city of about 100,000 people. Using new imagery acquired by Place in December 2023, we wanted to show how high-resolution imagery, coupled with machine learning, could give the council new insights into their city. Our analysis began with a positionally accurate true ortho, generated from an image collection comprising several hundred geotagged JPEGs, acquired over a few days of flying the city, with an unmanned aerial vehicle, or UAV. The imagery reveals the makeup of the city, with formal and informal neighborhoods, schools and facilities like athletic tracks all visible in high definition. Focusing in on one area of the city, Chirunga, you're able to see individual houses and their lots. The question is, how many people are there in this area of Chirunga? Place imagery provides the input for building detection, or more precisely building roof detection, using machine learning. You type in what you want to detect, and away you go. And the result? Buildings are output as discrete, smoothed polygons, as seen here in light purple. And how can this information be used to answer the question, how many people? According to the Malawi census of 2018, the average household size in Zomba is 4.2. To determine population, you simply multiply the number of buildings by household size. In this small area alone, machine learning detected 651 buildings, so 651 times 4.2 gives an estimated population of 2,734. And the utility of this information? Well, council planners can use these figures to better plan for service provision, whether it's waste collection, clinics or schools. And this can be done very quickly, using desktop computers in the council itself. Question 2. What's the risk of flooding? Anguilla is a small British overseas territory east of Puerto Rico. The capital, the Valley, is located in the middle of the island. Even though it's only about 3 square kilometers in size and relatively low-lying, it's still prone to flooding. To assess flood risk, we started with elevation information, or height of objects above the ground. Elevation is derived from Place aerial imagery. Represented as a digital surface model, all objects, whether trees or buildings, are assigned a height in meters. That height can be color-coded. Here we see reds representing the higher areas and greens the lower. Once you have the elevation information, you can then map catchment areas, or natural boundaries delineated by ridges or hills, within which surface water will drain into a common channel to form a river or stream. Even at relatively low elevation, water will still flow to a common channel. Here we see both the catchment areas, coloured polygons, and their channels, blue lines. While channels may not be visible when it's dry, when it rains, these are the courses that water will likely follow as it seeks a route to the lowest lying point in the catchment area. So how do you assess the flood risk? Well, from the aerial imagery, as we saw in the previous use case, you can use machine learning to detect buildings. You can then see if these buildings are in water channels or close to them. Buildings at the lowest point of a channel are most at risk, as water accumulates as it flows downstream, and flow will be exacerbated if parts of the catchment area are impermeable. And by deriving an elevation profile, you can estimate water volume as it flows down from the highest to the lowest point in a catchment and determine whether the existing drainage system can cope. All of this means decision makers can efficiently assess flood impact and consider revising planning regulations or updating building controls. Furthermore, as buildings are often underwritten by loans and insurance, recording building characteristics, a task facilitated by combining place-street imagery, means it's possible to make a determination of the financial impact of flooding as well. Even in this small area of Anguilla, the likely cost resulting from flooding to buildings and damage to fixtures and fittings can be expected to run into hundreds of thousands of dollars.